A lot of our thinking so far has gone into constructing algorithms for the problem of computing marginals in a graphical model. But as we previously discussed, a very different type of inference problem, but one that has many applications in itself, is that of finding a single coherent joint assignment that has the highest probability. And we showed already that that doesn't have the same, that you can't just solve the marginals problem and pick the highest probability assignment for each variable, and that gives you the map assignment. That's not what happens. And so we need to have a different set of algorithms for solving the map problem, and we're going to talk now about the first of these, which is effectively following the exact same lines that we did for exact inference for computing marginals, only it turns out that one can repurpose them with a small change to computing the map assignment. So the first operation that we need to do in order to get this to work is we're going to take products and turn them into summations. And we're going to be doing that by observing that our distribution P of phi is proportional, as we know, to a product of factors. And if we're trying to find the argmax of that particular product, it can also be reformulated as the argmax of a summation, where each of these theta k's is the log of the potential phi of k, which is basically the same as taking the table that represents the factor and converting each entry into its logarithm. And that gives you something that, rather than being a product of factors, is a sum of these log factors. And there's really good reasons for doing that. First, because summations are easier to handle than products, but also because if you're multiplying a whole bunch of very small numbers, you're going to get numerical underflows. And converting this into summations is a much more robust algorithm numerically in terms of a practical implementation. And so now we're going to consider the problem that we just wrote here, which is the argmax of an expression that we're going to call theta of x1 up to xn, which is defined as the sum of factors over smaller scopes, which are these theta k's. And this is the example that I meant to show a moment ago. So this is taking a factor over scope A and B and converting it to its log factor by taking log base 2. And you'll notice that the numbers were carefully selected to give me nice outputs, but that doesn't have to be the case. Okay. So now that we've reduced the problem to one that we're taking the max over summation, we're going to now go back to our simple example of a chain, and we're going to think about how we can do max sum variable elimination in chains. And this is going to look almost identical to the sum product algorithm that we had before. So let's understand what we're trying to do here. So assuming that what we're trying to do now is forget the argmax. Let's assume that we just want to find the max of this expression theta of A, B, C, D, and E. And so just like in the sum product case, we can break up the maxes into a max over A and then a max over B and a max over C and a max over D. And while we might not be quite as used to doing this kind of operation that I'm about to show, it's equally valid to point out that because none of these guys, theta 2, theta 3, or theta 4, depend on A, we can add them up to the max over this guy, over theta 1 of AB, after computing the max. And so that's going to give me a factor here, which looks like max over A, theta 1 of AB. And I'm going to call that lambda 1 of B, because notice that this is not a constant, it's a function that depends on B. For different values of B, you're going to have different A's that maximize and different values of the max expression. And so this lambda 1 of B is simply the max over A of theta 1 AB. And that process has effectively now eliminated A from this expression and given me a maximization problem over one fewer variable, only B, C, D, and E. Just like in the context of sum product algorithms, we can view all of these operations as operations over factors rather than just thinking about them in terms of expression. So whereas before we defined things like factor product and factor marginalization, we can now define analogous operations that correspond to factor summation and factor maximization. So factor summation, a very obvious operation, does exactly what we did here. So if we wanted, in the case of factor product, if we want to define the row for A1, B1, C1, we're going to add up the entry 3 from A1, B1, and the entry 4 from B1, C1, and that's going to give me 7. And I can similarly define all of the other entries in the factor summation, which we're showing here on the right. Factor maximization is the same way that we could sum marginalize a factor. This is something that max marginalizes. It's called max marginalization. And what it does is it looks, so I'm trying to get rid of B, I have these two rows here, say for example, A1, B1, C1, and A1, B2, C1 that only differ on B. And my new entry here, A1, C1, is going to be the max of these two entries over here, which in this case is going to be 7. And similarly for, say, A1, C2, I'm going to end up with a max of 4.5 and 2, which is 4.5. So this is another form of marginalization where I remove the variable B, but using an operation other than summation. So now that we've defined these two operations, we can go back and define the max sum variable elimination in chains as a set of factor operations, where I eliminate A, then B, and so on and so forth. So for example, having eliminated A as in the previous step, I can now do the exact same operation by noticing that the only factors that depend on B are theta 2 of B and lambda 1 of B. So these other two I can move outside of the maximization. And that's going to give me a max over B of a factor that is the sum of the two factors theta 2 BC and lambda 1 of B that I got from the previous elimination step. And that's going to give me a new factor, lambda 2 of C, and the process continues in exactly the same way as variable elimination did for the case of sum product. And that's basically the algorithm. So now let's think about what we get at the end of this execution for the final factor. So what is lambda 4, having gone through lambda 2 and lambda 3, now we get lambda 4 of E. What is lambda 4 for a given value little e? Lambda 4 of little e is what we got by maximizing over A, B, C, and D of theta A, B, C, D, and E. So this is the best possible assignment, the best value that I can get, that I can possibly get, if we mandate that E equals little e. Okay? And so this is a factor, and it gives me that value for each one of the values, a score, effectively, for each value little e of E. This is called a max marginal. In the same way that we took variable elimination for sum product and we use that to define a clique tree algorithm, we can do exactly the same thing for max product, or max sum, using the exact same type of data structure. So here we're going to use the exact same clique tree, and we have cliques over AB, BC, CD, and DE, and we're going to, as usual, assign the potentials to the appropriate cliques using the family preservation property. And now let's go ahead and see how messages are passed in this clique tree architecture. So initially, the AB clique is going to define the message lambda1, 2, which is obtained by maximizing out A over theta 1, and the resulting message over B gets passed to clique 2. Clique 2 can take that message, multiply it with its own factor theta 2, and add that. This is max sum, remember? I'm going to add that to lambda 1, 2, and that gives me the message lambda 2, 3. And the same thing can happen when clique 3 passes a message to clique 4, in this case over the scope D. So exactly the same message passing process, except using max and sum instead of sum and product. We can equally well pass messages in the other direction. So 4 to 3 over scope D, 3 to 2, and 2 to 1. And all of the properties that we said hold in the context of sum product clique trees hold here as well. First, notice, for example, that once this message lambda 1, 2 is sent, it never changes again. It's defined once and for all. Lambda 2, 3, once it receives the message lambda 1, 2, it too has stabilized and will never change. And similarly for lambda 3, 4. So we can do one pass from left to right to compute all of the left to right messages, and a similar pass right to left to compute all of the right to left messages. And as soon as we do that, they've all converged. The second thing to notice is what is the value of this clique over here. So if we look at this, we can see that when I finally get all of the messages from both sides, I have integrated in theta 1, theta 2, theta 3, which is stored in the clique itself, and theta 4 coming in from the message on the right, and maximized out all of the variables A, B, and E, so that what I have left is a factor over the clique 3, which is the max over A, B, and E of the sum of all of the factors in this network. So just to summarize, once the clique I receives a final message from all of its neighbors except CJ, then that message is also final, will never change, and the messages from all leaves are immediately final. And so what we have is an algorithm that at convergence, that converges after 2 passes and gives us correct max marginals at every single one of the cliques. So let's take a simple example just to convince ourselves that this is doing the right thing. So I'm looking now at a much simpler network that only has A, B, and C. So there's 2 factors, 1 over theta 1 of AB, and theta 2 of BC. And first, we're going to construct the overall map theta, which is the sum of theta 1 and theta 2. So this is a factor summation went into this expression. And let's look at it and see what is the map assignment in this example. And if we just look at the numbers that we computed, we see that the map assignment is A1, B1, C1 with a value of 7. Now let's look at the message passing process that you would have on this very simple clique tree with 2 cliques. So this is theta 1, it's assigned to clique 1. Theta 2 is assigned to clique 2. And let's look at the 2 messages that are passed. So here was my A1, AB passes a message to BC, and that message is the max marginal or max marginalization over the variable A. And so we can see that here we have a max between 3 and -1, so we get 3, because this is the max over the 2 values of A that are consistent with B1. And for B2, we have the max over 0 and 1, so we get 1. And exactly the same process gives us for this message, where I'm max marginalizing C, I get this message that's passed from left to right. Now each of these 2 cliques takes its message. Notice that I've gotten immediate convergence here because there's only one message to pass in each direction. And so what I get here is the sum of this factor plus the incoming message. So I've added these 2 together. And so I have, for example, for the first row, A1, for A1, B1, I have 3 from here and 4 from here. So I get 3 plus 4, which is equal to 7. For A1, B2, I get a 0 from here and a 2 from there. 0 plus 2 equals 2. And I can do exactly the same operation to get this factor on the right. I get that by summing up this with that, and I get this factor over here. And you'll notice that miraculously, the max in each of these factors separately is A1, B1 on the left and B1, C1 on the right. So sure enough, what I got here was the most likely assignment consistent with A1, B1, and over here, the most likely assignment consistent with B1, C2. And you'll notice if you go back and check, and I'm not going to do that right now, but if you go back and check this big table over here, you can convince yourselves that this doesn't only hold true for A1, B1. If you look, for example, at A2, B1, you'll see that what you get here, the value 3, is the value of the most likely assignment that is consistent with A2B1. So actually, let's go back and check that. So here is A2B1. We have 2 assignments consistent with A2B1. One is 0.5 and one is 3. 3 is the best one. And sure enough, the value that we get here is 3. So it all works.
So what can we say about this algorithm once it converges? The important thing is that we can compute beliefs at each clique that represent exactly the max marginals at that clique. So how do we compute these beliefs? Analogously to what we had in the context of sum product, we look at the factor assigned to the clique, which is the theta I, and we add to it the incoming messages. Before, you remember, we had the factor assigned to the clique multiplied by the incoming messages because we were doing products instead of summations. What does this belief encode? This belief is exactly the max marginal. So specifically, we can consider for any given assignment to the clique Ci, we can look at the score of the best possible completion to the clique Ci, and that is the value of the belief at that clique. So it's the max over all of the variables Wi that are not assigned to the clique. One important consequence of the fact that we have max marginals is that we get a calibration property here as well. So the cliques must agree on the variables that they share. So to understand this, let's look at these two cliques that we have in the simple two-clique example. And here are the beliefs that we had for clique 1 and for clique 2. It's the sum of theta 1 plus the incoming message over here, and theta 2 plus lambda 1, 2. And let's look at what the calibration property tells us. It tells us that, for example, if we look at the implications of this clique regarding the variable b, we would have that this clique tells us that the best possible completion for b1 has a score of 7, and the best possible completion for b2 has a score of 3. This clique, if we look at it, tells us that the best possible completion for B1 also has a score of 7, and the best possible completion for B2 also has a score of 3. So these two cliques agree regarding their regarding the variable in their shared scope, which is the variable B. So to summarize, we can apply in the context of max sum exactly the same clique tree algorithm used for sum product. Messages are passed in the same way. The clique tree is constructed in the same way. The only difference is that the message passing operations use max and sum as opposed to sum and product. Exactly as in sum product, convergence is achieved after a single up and down pass. And the result of that is a set of beliefs that represent max marginals at each of those cliques, where, as a reminder, the max marginals tell us for each assignment what is the score of the best possible completion to that assignment. We previously showed a clique tree algorithm for performing max sum message passing, but we didn't talk about how one can take the output of that algorithm and construct an actual map assignment. We just showed how we can get max marginals. So how do we compute a map assignment? Well, it turns out that this task is easy, as our examples already indicated, if the map assignment is unique. Because at that point, we have a single maximizing assignment at each clique. And we've already seen that the value of that maximizing assignment is the theta value of the map assignment. So in our example that we showed before, we had the A1, B1, C1 assigned as the map assignment, and we saw that A1, B1 was the maximizing assignment in clique 1, and B1, C1 was the maximizing assignment at clique 2. And we also saw that due to the calibration property, the choices that all of these cliques must agree, which means that it doesn't really matter whether we pick the value of B from this clique or from that clique, because they're going to give us exactly the same answer. So that's all well and good, but what happens if life is not as kind to us? So if the map assignment is not unique, then we might have multiple choices at some of the cliques, and we might have to make a decision. So for example, imagine that at calibration, at convergence of the sum product algorithm, we have these two cliques over here, and we can see that in this clique over here, we have two assignments, A1, B1, and A2, B2, both of which have the value 2. And in this clique over here, once again, we have two maximizing assignments. And the problem is we can't now look separately at each of those cliques and pick an assignment, because at that point we might pick, say, this assignment in this clique and this assignment in that clique, and now we have a conflict regarding the value of the variable b. And it's not just a matter of saying, well, okay, let's forget, for example, the fact that we picked the value b2 in this clique over here, because we also picked the value c2, and intuitively we can see that c2 goes with b2 and not with b1. So the value a1, b1, the assignment a1, b1, c2 is not a good map assignment. So what we need to do is we need to pick not this one, but rather B1, C1 in the second clique in order to agree with the first clique. And so what we see is that arbitrary tie breaking may not produce an actual map assignment. So how do we actually address this problem? It turns out there's two main choices in terms of the solution. The first is to tweak the problem a little bit so as to make the map assignment unique. So, for example, if we add a tiny random perturbation to all of our factors, then with probability that's effectively 1, there's going to be unique map assignment, at which point we can go ahead and use the solution that we had if the map assignment was unique. The second is to use a procedure that picks assignments one at a time, building a map assignment clique by clique. So we start out with the AB clique, we pick A1, B1, and then when we go down to the next clique down the line, we remember that we picked B1 and we only are allowed to now pick an assignment that's consistent with B1. And that turns out to be an alternative algorithm that whose complexity is effectively the same as that of calibrating the clique tree to begin with, and so is not more expensive. Each of these options is a very reasonable option, and both are used in practice for decoding the map assignment from a calibrated clique tree. One of the reasons for the
but also
increasing popularity of map inference is that there is a large subclass of map problems that actually allow tractable inference. Now, we've already seen one class of map problems that allows tractable inference, which is the graphical models that have low tree width, for which you can apply variable elimination or clique trees. But it turns out that besides that, there is actually a rich set of other subclasses that can be solved using efficient algorithms, often based on ideas from computer science theory. So let's look at some of these examples and see how we might go about solving them. One such important class of problems is that of correspondence or data association problems. Here we have two classes of objects, in this case the red objects on the one side and the blue objects on the other, and we'd like to find a correspondence or matching between them. And the fact that it's a matching means that each the assignment has to be one-to-one, so you can't have a single red dot match more than one blue dot or vice versa. So here, for example, is one such matching. And we may, in addition, require that all the red dots be matched or that all the blue dots be matched, which can't be done in this case. So what is the quality of a matching, given the set of possible matchings? So how do we select between them? So we have in the model a notion of the quality of the match between I and j, which we denote in this case as the parameter theta ij. And so our goal in this problem is to find the highest scoring matching, where the score is defined as the sum of the matches multiplied by the quality of their score. And we constrain the variables xij, these binary variables that indicate whether I is mapped to j, via the mutual exclusion constraint that we discussed earlier. Now, this type of problem is easily solved using bipartite matching problems developed in computer science theory. And it turns out that in the context of graphical models or probabilistic inference, this type of problem has numerous applications. So for example, we might have on the one hand, say the red side, a set of sensor readings from a number of, say, airplanes that we're trying to keep track of. And on the blue side, we might have a set of airplanes or objects that we've previously detected, and we'd like to figure out which sensor reading corresponds to which object. Or we might have features in two unrelated images, and we'd like to figure out which feature in image 1 matches which feature in image 2. Or if we're trying to do some kind of text analysis, we might have a set of entities, say people or organizations, that we're trying to reason about or learn something about, and we're trying to match mentions in the text to those entities, subject to the constraint that each mention corresponds to exactly one entity. So let's look at one example application of this, which corresponds to one of the examples that we showed on mentioned on the previous slide, which is that of 3D cell reconstruction. In this case, we have over here a cell that we are trying to assess the 3D structure of, and we're looking at various slices through that cell taken from different angles via a microscope. And so these are various two-dimensional projections of the 3D object, and we're trying to figure out from that the three-dimensional structure. Now, within the cell, we might have these little tiny gold beads that are that were put into the cell so that we can somehow register the different images of the cell to each other. So here, these are examples of two such real images, and these are the little gold beads. You can see them in the little circles. And what we'd like to do is we'd like to decide that this bead over here is the same as that bead over there. And once we have that correspondence, we can then compute the 3D reconstruction using some volumetric reconstruction algorithms. And in this case, the matching weights, those theta ij's that we saw on the previous slide, represent the similarity between this position, between this dot and this dot, in terms of the location in the image and in terms of the neighborhood appearance in the vicinity of that point. A very different application for what is effectively the same kind of idea is if we have, say, a 3D mesh scan of an object such as a human being, and we'd like to figure out how points on this mesh match up to points on a somewhat related but different mesh, whether it's different pose or different shape. So here we would like to realize that this point over here maps to this point over here, or that this point on this mesh maps to this point on this mesh. And once again, these matching weights, the theta ij, represent exactly the similarity of both location and, again, the local neighborhood appearance. Another very commonly used class of tractable map subproblems are those that involve what are called associative potentials. Associative, also called regular in some cases, or tractive, are cases where the variables that are connected to each other like to take the same values. So let's consider this example in the context of binary valued random variables, where we have a variable xi and a variable xj that are connected to each other, and we have the on-diagonal potentials, the 0, 0, and the 1, 1, which are the cases where xi and xj take the same value, and we have the off-diagonal potentials, 0, 1, and 1, 0, where the variables take on different values. And what we would like in an associative model is for the 0, 0 and 1, 1 cases to be preferred over the off-diagonal cases. And that can be formulated using the following constraint, in which we have that A plus D, which are the on-diagonal entries, are in sum greater than or equal to B plus C, so that in aggregate we prefer the on-diagonal to the off-diagonal entries. It turns out that if you have even an arbitrary network in terms of fully dense connectivity over binary variables that use only the singleton potentials and these pairwise potentials that are associative, they're also called supermodular, which is a term that comes from mathematics. If the pairwise potentials satisfy this constraint that we saw over here, then you can find an exact solution regardless of the network connectivity. And that can be done using algorithms from combinatorial optimization from computer science theory for finding minimum cuts in graphs. For non-binary valued random variables, exact solutions are no longer possible, but it turns out that very simple heuristics can get very, very high quality answers very efficiently. And so many related variants that are not necessarily binary admit either exact or approximate solutions. And specifically, we talked before about the class of metric MRFs, which occur a lot in computer vision as well as other applications. And it turns out that for metric MRFs, even over non-binary variables, you can use these very efficient algorithms. So one such example is in the context of depth reconstruction, where we have two views of the same object taken from slight disparities, say using a stereo camera. So here is view 1 and view 2 in the same scene, and you can see that they're slightly different from each other. And if we can, and we now have for a given, we're trying to infer the following image that tells us for each pixel in the image what is the actual depth, that is the z dimension. And one of the constraints that we'd like to enforce is that because of smoothness in the image, the z value for a pixel is similar to the z value of an adjacent pixel. And that allows us to clean up a lot of noise that might arise if we just try to infer the depth of individual pixels by themselves. And there are many other such examples in computer vision that are used quite commonly and use this kind of associative potentials. Examples include, for example, denoising of images, infilling of missing regions, and a whole variety of other tasks, including foreground-background segmentation, and so on.
Another kind of factor that admits efficient solutions is a cardinality factor. And this is a factor that in general can involve arbitrarily many binary variables x1 up to xk. But we're going to require that it's sparsely representable in the sense that the score for an assignment to x1 up to xk is a function of how many xi's are turned on. So to take an example, here is a factor like this over A, B, C, and D, and you can see that we have only 5 different values for entries in this factor. We have this pink entry over here when the sum of the xi's is 0. We have this blue entry over here that occurs when the sum of the entries is 1. So for these 4 entries, you have the purple one that occurs when we have 2 xi's on, the green that occurs when we have 3, and the dark blue that occurs when we have 4. Okay, so there's only 5 different possible values here, even though there's potentially 2 to the 4 different possible combinations. And it turns out this actually occurs in quite a number of different applications. When we talked about parity constraints, for example, in message decoding, parity constraints are something that only looks at the number of xi's that are on. If you want to do image segmentation and you want to have some kind of prior on the number of pixels in a given category, you want to say that in this image, we expect the number of pixels to be between, that are labeled sky to be between 30 and 70%. This is potentially a factor over all pixels in the image, but it only counts the total number of pixels. And so, again, turns out to be efficient. And there's many other examples as well. A different one that also turns out to be very useful in practice is the notion of sparse patterns. So here again, you can have an arbitrary number of variables x1 up to xk, but you only specify a score for some small number of assignments. So here, for example, is a factor again over A, B, C, and D, and I have now only 3 entries in that factor that get some value. They don't have to get the same value, but only they get some value, and all of the ones that are white are all have exactly the same score, generally 0. And this is actually surprisingly useful in practice because it's very useful to give a higher score to combinations that occur in real data. So for example, if we were doing a spelling problem, you want to give a higher probability to whatever letter combinations occur in a dictionary. And that's a finite number, it's bounded by the size of the dictionary. And now you have all the combinatorially many letter combinations that don't occur in the dictionary. You don't need to give them all a separate weight. And now it turns out to be, again, a sparse factor. The same thing actually occurs in image analysis problems, where, for example, you can look at all of the 5x5 image patches that actually occur in natural images. That's actually a surprisingly small set of patches relative to all possible 25 pixel combinations. And so once again, this is a very commonly used factor over that arises in practice. A different factor that has tractable properties is a convexity factor. Here we have binaries 1 up to xk that are denoted by these blue dots over here, but now they're ordered. So this is x1, x2, and xk. And the convexity constraint says you can assign these values, these variables 1 or 0, but you have to assign them in a way that only a convex set is assigned the value 1. So for example, you can have this set be 1 and everything else be 0, or you can have this set be 1 and everything else be 0, but you can't sort of have a scattered set of 1s that are interspersed with the 0s. And again, this occurs in a surprising number of applications. You can look at parts in an image segmentation problem and say that the parts should be convex. You can think about word labeling in text and say that the words labeled with a certain part of speech or a certain segment that corresponds to a part in a parse tree, for example, needs to be contiguous in the sequence. If you're trying to label a video with a bunch of subactivities, you can say that each subactivity needs to have a coherent span with a beginning and an end, for example. So to summarize, there is many specialized models that admit a map solution using tractable algorithms, and a surprising number of those do not actually have tractable algorithms for computing marginals. And these specialized models are useful in many cases on their own, like the matching problem that I showed, but also as we'll see as a component in a larger model with other types of factors. And the fact that this as a submodel has a tractable solution will turn out to be very useful as well. We previously defined the map inference problem, which is that of finding the highest probability assignment to a graphical model. And we talked about particular classes of models for which the map problem was tractable. One was a class of models that had sufficiently low tree width so that one could use techniques such as variable elimination or clique tree methods. And then we also talked about a variety of other special purpose classes where one could do tractable inference. What we're going to talk about now is a general purpose algorithm that can be used to solve any map problem, keeping in mind, of course, that the map problem is an NP-hard problem, and so you're not going to get a fully polynomial time algorithm that one can utilize in the context of any problem. So the class of methods that we're going to talk about is called dual decomposition. And it's derived from the increasingly prevalent view of the map inference problem as an optimization problem and building on techniques from the field of optimization theory. So let's go ahead and first reformulate the problem in a way that makes it amenable to this kind of analysis, and this is just a convenience. So here we're going to assume that the map problem that we're trying to optimize. Remember, we've reformulated this as a max sum as opposed to a max product, which is a convenient reformulation. And we're going to assume that the theta that we're trying to optimize is comprised of a sum of two different kinds of factors. The first is singleton factors, which are over the scope of a single variable, xi, and the second are larger factors that are over the scope of multiple variables. And clearly one can fold in the singleton factors into some larger factor that contains the variable in its scope, but it turns out to be convenient to keep them in the model for reasons that will become clear in a minute. So now our goal is to find the value for the moment. We're going to talk about how to find an actual assignment in a little bit, but imagine that our goal is to just figure out what is the value of the highest probability assignment x. And so we're trying to find the x that maximizes this total summation. So one thing that we could do, which would be wrong, but we could do it, is to say, well, let's forget about the fact that we're trying to do a single joint assignment. Rather, we're going to think about each problem with blinders on. So we're going to think about each theta I xi by itself, and we're going to find the xi that optimizes that factor, and we're going to do the same for the larger factors. Now, that, of course, is going to be a very poor solution because the xi that's going to optimize one theta I is going to be completely inconsistent with the xi that is selected by one of the larger factors that contains xi. So you're going to get a completely incoherent joint assignment. It's not going to be a joint assignment. It's going to be a bunch of different assignments that don't agree with each other. So what dual decomposition does is it's going to try and do the same kind of divide and conquer, but it's going to do it in a way that tries to force these local decision-making problems to agree with each other. And so how are we going to do that? We're going to do that by introducing a set of costs. And the costs are going to be things that are going to drive each of these local problems to hopefully eventually agree with the decisions made in other local problems. So going back to this, what we're going to do, and now this is actually an equality, is we're going to do the following. For the variable I, we have its own local potential, theta I, and then we have a bunch of costs. And these are the costs that are derived from and we have a cost for each factor f that contains I in its scope. And that cost is going to try and pull the little I decision maker, which is called a slave, by the way. Each of these decision problems is called a slave. So this is the I slave. And here is a little term that's supposed to pull the I slave to agree with the decision made in factor f. Similarly, we have an f slave. And what we're trying to do is we're trying to get the f slave to agree with the I slaves for the variables xi in its scope. Now, as written over here, let's convince ourselves that this expression is in fact equal to the first line. And the reason is that here I add a term lambda fi of xi for I in the scope of f, and here I subtract that same expression over here. So each of these expressions, lambda fi, gets added in at I and subtracted out at f, and so they cancel out. So far I've had equality, but now I'm going to really let each agent make their own decisions. So now, before there was still the maximization on the outside, now I'm going to let each agent look at its little set of factors that it owns, including the sort of penalty terms that it has in order to agree with the other slaves. And each one is going to make its separate optimization with all of those terms together. So you can think of these penalty terms as messages from or between f and I. They're their way to communicate. For f to communicate to I what it thinks ought to be done, and for I to communicate with f at the same time. Now, one important point that we'll come back to in a little bit is that this function here, which is called L of lambda, notice that this is a function of lambda, and only a function of lambda because it's no longer a function of x because I've maximized over the x. So you're going to get a different value of this function depending on the choices of the penalty parameters. This function is an upper bound on map theta for any value of lambda. Now let's understand why that is. We've seen in this line over here that this is actually equal to that. Okay? We've shown that everything cancels here. And what I've done here is, over here I'm forcing a single x to maximize this entire expression together. And here I'm letting each term be optimized separately. And that gives me more degrees of freedom because here I had to pick the same x across the board, and here this one gets to pick one x, and this one gets to pick another value of x. And so since the assignment where they all agree is one of the assignments that can be considered in this optimization problem over here, the overall value that can be gained is only higher than if I had to force them all to agree, which is a more constrained optimization problem. In general, the more constraints I have on the space that I'm optimizing, the lower the value that I can get. So introducing some notation, which we'll use in the rest of this presentation, we're going to call the function that the ith slave is optimizing theta I lambda, and the function that is being optimized by the f slave theta f lambda. So let's take an example to make this a little bit more concrete, because this was a little bit abstract. So let's go back to our example of a four-way loop where we have x1, x2, x3, and x4. And we're going to have these four pairwise potentials, which we're going to denote with letters this time to disambiguate indices a little bit. So we have theta f of x1, x2, theta g of x2, x3, theta h, and theta k. So now how is this decomposition going to work here? Let's assume for the moment that we're going to decompose this over edges. So our factors are going to be, for example, the edge x1, x2. So now what is the optimization problem that this factor chooses? Well, it has its own potential, theta f x1, x2, and then it's going to have these little costs that are going to try and get it to agree with x1 on with the one slave on x1 and with the two slave on x2. We're similarly going to have for x1, x4, this is the k, so this is the f slave. This is the k slave, and it's going to have its own potential, theta k, and two penalty terms that are going to try to make it agree with the one slave on x1 and with the four slave on x4. And we similarly have exactly the same form for the other two slaves, the g slave and the h slave. In addition, we have slaves for the individual variables, the 1, 2, 3, 4 slaves. So here is the one slave, and notice that the one slave has its own potential theta 1 x1, and at the same time it has these two terms that are trying to make it agree on the one side with f, which is over here, so this is because of this, and on the other side with k, because of that. And the same thing applies to the other slaves. So the 2 slave, for example, is going to have to agree with f, and is going to be incentivized to agree with f and with g. So it has a lambda f2 and a lambda g2. Now, I've done this in the context of a very simple scenario where I've broken up my model into the factors that existed in the original specification. So, for example, I had factors that were pairwise potential, so I had a slave for each such factor. But that doesn't have to be the case. In fact, the only constraint that I need to satisfy is that I need to define a slave to be defined as a subset of factors that admit a tractable solution, so that each one can be optimized efficiently when considered in isolation. So, for example, if we return to this network, say one thing we could do is we can introduce 2 larger slaves instead of the 4 smaller FGKH slaves, which One is corresponding to F and G together, so this is the FG slave. And the other one representing the KH slave. And in this case, if we think about the agreement, we still have the 1, 2, 3, 4 slaves that represent the individual variables. And so now we're going to have to require that theta F agrees with X1, with a 1 slave on X1, with a 2 slave on X2, and with a 3 slave on X3. And so we have this expression which has a lambda term for each of those 3 variables. And we have a similar term for a similar expression for the KH slave, where in this case, the KH slave has to agree with the 1 slave on X1, the 4 slave on X4, and the 3 slave on X3. If we now think about the singleton slaves, for example, X1, we see that X1 has to agree with the FG slave, so there's a term to encourage that, and with the KH slave because it's present in both. On the other hand, the X2 variable only occurs in the first slave, and so it only has a single agreement term with the FG slave. And similarly for X3 and X4. So how do we then construct the slaves? In pairwise networks, what we typically do is we divide the factors into a set of disjoint trees. And this is, in fact, what I showed in the previous slide. We divided it into one tree that went through the first wedges and the second one that went through the second wedges. And they're disjoint, which means that every edge factor is assigned to exactly one tree. And because they're trees, we know how to optimize them efficiently using techniques like variable elimination or clique tree. But we also discussed that there's other classes of factors that offer tractable inference. So for example, we talked about matchings or models that are associative or regular or supermodular or whatever we call them. And all of these are tractable classes, and we can take a whole bunch of factors that fit into one of these tractable categories and optimize them together in one fell swoop. We don't need to divide into separate edges.
So let's look at an example of this. Remember a while ago we talked about the problem of 3D cell reconstruction, where we have a cell over here that we're imaging, and we're taking various images that are slices, two-dimensional slices through that cell, and we'd like to reconstruct the three-dimensional structure. So here, as we discussed, we have the slices, and we would like to correspond the beads that we see, these little gold beads that we see in these different images, to each other. So try to figure out that this bead corresponds to this bead over there. And from that, we can then subsequently obtain the 3D reconstruction. Now, when we last talked about this, we described this as a matching problem, where the matching weights between a point here and the point here are derived from the similarity of both the location in the 2D slice and the appearance of the local neighborhood. But it turns out that neither of these is sufficiently distinctive in order to really make that determination robustly, that one point in an image matches another point in the other image. And so in order to do this with a reasonable success, we need to have another set of potentials, which are pairwise potentials, which basically preserve distances of these marker positions. So tell us that if we want to correspond this point over here to this point and this point to that point, then the distances between them should also roughly be preserved. Now, this set of potentials is relatively sparse and therefore can be solved usually using exact inference. This set of potentials is not complicated on its own because it's a matching problem. If you put them together, it turns out to be a difficult problem to solve. In fact, you can show that a joint set of potentials like this with these two different categories is in general NP hard. But using dual decomposition, we can solve each of these separately and then communicate information between them. So each of these would form a tractable slave. We previously defined the intuition for the dual decomposition algorithm, which takes an optimization objective and decomposes it into a bunch of different slaves and uses communication between the slaves to try and get them to agree with each other about the overall map assignment. So now let's take this intuition and convert it into an actual algorithm. So what we have here is each slave gets its own pet objective function. So here is the objective function for the ith slave, for the slave corresponding to the variable xi. And here is the objective function that the slave corresponding to the larger set f is trying to optimize. Now, each of these initially has as a component its own local objective function that is assigned to it. But in addition, we're going to introduce for each of those a set of terms, these terms, that modify its objective function so as to try and get it to agree with the other slaves. Specifically, we're going to try and get the I slave to agree with the factors f in which I appears, and conversely, we're going to try and get the f slave to agree with the slaves of the variables in its scope. So let's see how that gets done. We're going to initialize all of these incentive terms, all of these lambdas, to be 0. Initially, each slave makes its decision based purely on its own local piece of the objective. But then, as the algorithm evolves, these incentives start to change. So how does that happen? At each iteration t, each slave optimizes its current objective. So the ith slave optimizes theta I hat lambda, where lambda is the current set of the penalties, the current set of penalties. And that gives it an assignment which we're going to call xi star. The f slave does the exact same thing. It optimizes its own local objective, which is theta hat f, also using the same set of lambdas, and that gives it x star of f, which is this guy over here. Now, let's see what happens if there is a disagreement between a large slave f and a variable I in its scope. What we would like to do is we would like to incentivize them to agree with each other. And so what we do is that for all f and all variables I in f, if they disagree, that is, if the chosen variable for xi in the assignment chosen by the factor f is different from the assignment of I chosen by the I slave, then we need to change their incentive function. And we do that by basically changing the lambdas. And so specifically, we see that here, when we look at the penalty for the pair Fi, which is over here, we decrease alpha t, we decrease by a factor alpha t, which is greater than 0, the preference for xi star, which is the value chosen by the I slave. And if we see that, if we look at that, we see that that's going to disincentivize the I slave from picking the value that it picked. Conversely, we increase the preference for the value chosen by the F slave, which is this value over here, by the same amount, alpha t. Now, that changes the preference of the I slave, but it also changes the preference of the F slave by the exact same amounts, but in the opposite direction, because notice that here we have a negative sign, whereas here we have a positive sign. So it makes both the I slave and the F slave move in the same direction, move in opposite directions so as to agree with each other. So what happens as we continue doing these iterations over time? Well, one can show that under fairly weak conditions on these parameters alpha t, the lambdas are guaranteed to converge. What are these conditions? The alphas need to be big enough so that they make a difference, so that if we sum up all of the alpha t's for all t, we end up with a diverging sequence that sums to infinity. On the other hand, they need to be small enough so that we eventually achieve convergence, and that is obtained by this second condition on the summation over here. Now, in fact, one can also show that not only do we get convergence to a unique global optimum regardless of the initialization. So the lambdas always converge. Now, the question is, what are the implications of that, of the convergence of the lambdas? And so what happens at convergence? At convergence, you can show that there's no more change. And so at that point, each of our slaves has its own locally optimal solution over its own variables, the ones that are in its scope. So is that good enough? Unfortunately, not always. That is, even though we have achieved convergence, the solutions of different slaves may or may not agree on the variables that are shared between them. However, if they do agree, if we can get all of the slaves to agree with each other, we can show that the shared solution is a guaranteed map assignment. So if the slaves agree, we have effectively solved our initial optimization problem, which is that of finding a map assignment. If that doesn't happen, that is, if the slaves have not agreed on their shared variables, then we need to solve what is called the decoding problem, where we need to somehow put together these different solutions that the different slaves have converged to and come up with a single joint assignment. So how do we do that? How do we solve this so-called decoding problem? It turns out that people have constructed a range of different solutions for this, none of which have particularly strong performance guarantees, but they often work quite well in practice. So, for example, if we use a decomposition of the original problem into spanning trees, then each of the spanning trees covers all of the variables, so we can take the map solution of any individual tree and say that that is an an assignment to all of the variables. So that's one approach. A second approach that is not a winner takes all is to have each of our slaves vote on the xi's that are in its scope, and then for each xi you just do the majority voting. So that's another approach. A different approach uses some kind of weighted averaging of the sequence of messages that are sent regarding each xi through the course of the iterations of the algorithm. So each of these works reasonably well, but what it turns out that the right solution is to simply use multiple solutions and then pick the best one. And the critical observation here is that the scoring function theta for any assignment is something that we can easily evaluate. So why not do all of these and use multiple trees and generate a whole collection of x's and then evaluate theta x for each of those solutions and then pick the best one. And it turns out that when you do that, you generally get solutions that are better in terms of their overall score than any fixed strategy.
Now, the other nice aspect of this analysis comes back to a point that we made earlier in this module, which is that for any lambda, this function that we defined as L of lambda is an upper bound on the value of the true map assignment. Now, what does that imply? It means that if you give me any x that you think is a reasonable candidate, so this is a candidate for the map assignment. Now, by definition, it's either equal to the map or it's worse than the map. So whatever the score is, theta x is going to be less than or equal to the value of the map assignment, because it certainly can't be any better than the true maximum. And that in turn is less than or equal to L of lambda. Now the point is that this is a mystery. We don't know the value of the true map assignment, but we can compute this and we can compute that. And that gives me a bound on how bad my current assignment is, because I know that the difference between the true map assignment and the score of my assignment is no worse than the value of L lambda minus the score of my assignment, which means that I can look at the difference between my assignment score and L of lambda. And if it's small enough, so if this is small enough, I'm happy, even though I might not have the true map assignment, because I know that I'm close enough to the point that I don't care anymore. And so that's a really nice guarantee because it allows me to sort of stop and say, good enough. I don't know if I'm at the optimum, but where I am, I'm happy. So what are some of the important design choices in implementing dual decomposition? First, there is the division of the problem into slaves. In general, not surprisingly, larger slaves that incorporate more factors are more expensive to optimize because you're solving a more complicated optimization problem within each slave. But on the other hand, they can be shown to improve convergence and often get you closer to the true map assignment. A second design choice is how to select the locally optimal solution for the slaves. In many cases, a slave might have more than one optimizing assignment, and some of them might be more in agreement with other slaves than some. And so how do you pick within the set of equally good slave assignments the one that's going to get you to convergence faster? The third, which we've briefly mentioned before, is how do you adjust the step size alpha t so as to move things towards convergence fast, but still slow enough to generate convergence. There's some hard and fast rules that guarantee convergence, but they're often quite slow, and there's clever rules that still guarantee convergence and tend to work better in practice, and this is an active area of research that's ongoing right now. And then finally, we've talked about the decoding problem and the fact that there's many heuristic choices there, and so that's another design choice that one needs to make when implementing dual decomposition. So let's summarize different aspects of what we've talked about. First of all, let's summarize the algorithm. Dual decomposition is a general purpose algorithm for map inference that works by dividing the model into tractable components that could be potentially multiple factors in a single component or slave, solves each slave locally, and then passes these lambda messages between them to try and get them to agree. And we've talked before about the presence of tractable map subclasses. Any tractable map subclass can be used in this setting as a slave to allow slaves to be large and richly structured as opposed to just little tiny factors that are going to be only making very myopic decisions based on minimal information. One of the nice things about the dual decomposition algorithm is that it has a lot of theoretical backing to support it. So formally, and we're not going to go into the details of what this means, but just mention what this is actually doing from a formal perspective. This is a subgradient, which is kind of like a gradient optimization, but not exactly. A subgradient optimization algorithm on a problem that is a dual problem to the map problem. And if you didn't understand that, that's okay. This is just sort of a pointer for those of you who might have seen some optimization before to kind of fit this into that world. But this view does provide some important guarantees, some of which I've mentioned in this presentation. First, it gives us an upper bound on the distance to the between where we are in the true map assignment. And it provides us with conditions such as agreement among all of the slaves that guarantee a condition under which we have actually found a true exact map solution. And there's even some interesting analysis, which I'm not going to present, that tells us when one decomposition of the model into slaves is better than a different decomposition of the model into slaves. Now, in practice, this algorithm has some significant pros and cons. On the pros, it is very general purpose. You could really use it for any model if you're willing, for example, to decompose the slaves fine enough. Of the algorithms that are currently out there, it provides some of the best theoretical guarantees in terms of convergence properties. And because of the way that it's structured, it can use these very fast specialized map subroutines for solving large model components like matching problems, for example, or subsets of edges that are submodular or associative. On the other hand, it's really not the fastest algorithm out there. That is, there are algorithms that, when they work considerably faster than the dual decomposition algorithm. And more so than most, it has a lot of tunable parameters and design choices, which make it a somewhat finicky algorithm to apply in practice because one has to play around quite a bit in order to get good performance.